Hello student, today we are going to start our next part of AC. We'll go for quick recap of the thing which we have done earlier on. We did average value of the current, that was equivalent to what? Im upon, this is Im into 0.637 I naught. That was average value of the current or mean value of the current. And mean value of the EMF was 0.637 I naught. We also did RMS value of the current, that was basically equivalent to what? It was I naught upon root 2. And RMS value of the EMF was what? It was E naught upon root 2. We also did the phase relation between current and EMF in the case of resistance, inductor and capacitor. That was like phase difference in the case of resistance was basically how much? The phase difference was 0. Means what? It was E naught sin omega t, then current was I naught sin omega t. Then we had in the case of inductor, what we had? That is E is equivalent to E naught sin omega t, then current was equivalent to I naught sin omega t minus pi by 2. In the case of inductor, current lagged behind EMF by pi by 2. Similarly, in the case of capacitor, what we had? That was E is equivalent to E naught sin omega t. In this case, current leads EMF by pi by 2. This is all derivation we did in the AC part 1. Now we'll be continuing with the second part of it. That we'll start with the power consumption in the case of resistance only. See, power consumption in case of resistor only. See, we know that power is basically what? Power is rate of doing work. Work delta W by delta T. And we know that power is also written as E into I. And what we are doing is that we are considering the case of resistance. We know that in the case of resistance, what we have? E is equivalent to E naught sin omega t and I is basically equivalent to I naught sin omega t. What we will do is that we will place this value and integrate it out. What do we have? In place of E, we can write E naught sin omega t. In place of I, we will write sin omega t, and this is what? Delta t will go to this side. And what we will do? This is E naught into I naught. Will integrate sin square omega t delta t 0 to t. What is the integration of sin square omega t? In that case, what we have? We do not have direct formula. We'll utilize trigonometry over here, and it is coming out to be what? 1 minus cos 2 omega t upon 2 delta t. It goes from 0 to t. See, what we'll do is that we'll place the values over here. We'll place 0 to t delta t. This is 0 to t integration of cos 2 omega t delta t. See what we get. This is E naught I naught to integration of delta t is how much? It is just t, and it varies from 0 to t. Then what will happen? We will write capital T, it doesn't matter. And integration of cos 2 omega t will be equal to what? Sin 2 omega t upon 2 omega, and you go from 0 to t. See what will happen that suppose we place the values over here, it is coming out to be this, and over here when we write it out these values, what we have? This is sin 2 omega t minus sin 0. See, sin 0 is 0 and this is what? omega t is 2 pi, this is 4 pi, sine 4 pi, and we know the sine and pi is 0, whole of this is going to be 0. So what will we get? This is, we have to calculate the power. Basically this is work and this is upon our time. This becomes what? E naught, I naught. What we will do is that 2 will write in terms of like root 2. So then it becomes what? EB into IB. That's it. This is the power consumption in the case of resistance only. Similarly, what we'll do is that we'll go for power consumption in the case of inductor. We have, suppose, let us suppose we have inductor, power consumption in an AC circuit containing inductor only. See, in the case of inductor, we had derived the relation that was what? That is E naught sine omega t, and current lagged behind EMF by pi by 2. So suppose we go for like power consumption in the case of inductor only. What will happen? Power, we know that it is equivalent to rate of doing work. And what is this? It can also be written as E into I. And over here, what we have E as? E naught sin omega t, and this is I naught sin omega t minus pi by 2. See, we have to calculate the work done. It is what? This is E naught, this is I naught. What we'll do is that this is sin omega t. This can be written as what? It can be written as minus cos omega t. See, what we'll do is that we will integrate it out for the interval 0 to t. In this case, what will happen? The integration of sin omega t cos omega t, what we can do is that we can divide and multiply by 2. In that case, it becomes easy. See, this 2 sin theta will become what? 2 sin theta cos theta will become sin 2 omega t, and we need to integrate it still over here. And what is that? This is E naught I naught upon 2. Integration of sin 2 omega t is what? Cos 2 omega t upon 2 omega. It goes from 0 to t. See what will happen over here. When we place these values, it is coming out to be what? 4 omega. This is cos 2 omega t minus cos 0. And both are 1. 1 minus 1. So, the power consumption in the case of circuit containing inductor only is going to be 0. Now we go for power consumption in the case of capacitor only. This is capacitor. It's connected to AC. We'll go for power consumption in an AC circuit containing capacitor only. See, in the case of capacitor, we had calculated out the phase relation between EMF and current. In that case, what we had, EMF was E naught sin omega t, and current led EMF by pi by 2. So what will happen? We'll have suppose we need to calculate power. Power is basically what? Delta W by delta T. This is what? E into I, which can be written out as E naught sin omega t. This is I naught sin omega t plus pi by 2. This is delta W. What we can do? We can transfer this delta to this side and we'll integrate this out. It is coming out to be what? This is E naught I naught then we have sine omega t, then this sine omega t plus pi by 2 can be written as what? Cos omega t delta t, and we'll integrate this out from 0 to t, and it is quite similar to this integration which we have done earlier. It is, what we will do is that we do not have direct formula for integration of sine omega t cos omega t. What we will do is that we will utilize the trigonometry over here. So it becomes easy. We divide by and multiply by 2 sine omega t cos omega t delta t 0 to t. See, it is coming out to be what? E naught into I naught 2. This is sine 2 omega t delta t. We integrate this out. It is E naught I naught 2. This is what? Minus cos 2 omega t upon 2 omega. It goes from 0 to t. When we place these values over here, it is coming out to be what? It is cos 2 omega t minus cos 0. In this again, we have this equivalent to 1, this is minus 1, it is going to be 0. So we see that in the case of inductor as well as capacitor, the power consumption is 0. Now we'll move for power consumption in the case of LCR circuit. We'll go for power consumption in LCR circuit. Means the circuit contains all the three elements: inductor, capacitor and resistor. We have topic is power consumption in an AC circuit containing LCR circuit basically. We have all the three elements. In this case, let us suppose E is equivalent to E naught sine omega t. And what we will do is that, let us suppose the phase relation with them is phi between current and EMF. It is sine omega t. This is phi. Again, we'll move on to like what is power consumption. It is delta W by delta T, and this is E into I, and we have the values. This is E can be written as E naught sine omega T, and I can be written as I sine omega T plus phi. Since we have to calculate the work done, what we will do is that E naught I naught. This is what we have. This is sine omega T. This is sine omega T plus phi, and we'll transfer this to this side to integrate. See, in this case what we have no problem with this. We have problem with this. What we'll do is that we'll expand it out utilizing the formula sin A plus B. That is what? Sin A cos B plus cos A sin B. So it becomes what? This is sin omega T. This is cos phi. This is what? This is cos omega T. This is sin phi delta T. See, what we'll do is that we'll have like E naught into I naught. This is what we get. This is constant cos phi, and we'll go for like 0 to t sine square omega t delta t. Then what we have? We have E naught into I naught. This is sine phi. This sine get multiplied by this cos omega t. This means we need to integrate sine omega t cos omega t delta t. Clear? So what we'll do is that we'll integrate this also, we'll integrate this also. See, in this case what we have, this is E naught, this is cos phi, integration of sine square omega t. Again, we do not have direct formula. We'll have to utilize a bit of trigonometry over here to make our life easier over here. See, this is E naught, I naught, this is sine phi. Again, what we'll do is that it multiply and divide by this 2 sin omega t cos omega t delta t. See what we have. This is E naught I naught cos phi. This is 2. We need to integrate 0 to t delta t, and we need to integrate 0 to t cos 2 omega t delta t. Then we have E naught I naught sin phi upon 2. This can be written out like 2 sin omega t cos omega t can be written as sin 2 omega t. This is what? Sin 2 omega t delta t. Now what we'll do is that this is like, this is E naught I naught, this is cos phi, this is 2, this is t, it goes from 0 to t. Then we have what? This is sin 2 omega t upon 2 omega, it goes from 0 to t. And similarly we go for integrating this E naught I naught, this is sin phi upon 2, integration of it, this is what? Cos 2 omega t upon 2 omega, it goes from 0 to t. See over here we know that the values, when we place it out over here, omega t minus sin 0, these both are becoming 0. In this case also what we have, placing this value 2 omega t minus cos 0, it also become 1 minus 1. So it won't contribute anything, it won't contribute to anything. What do we have? This is delta w, will bring this t to this side, and this becomes what? E naught I naught. 2 we can write it like root 2 into root 2, and we'll have cos phi, which we can write as EV into IV into cos phi. This is the power. This is the power consumption in the case of circuit containing our this is the LCR circuit basically. It's clear? Now we'll go for see, we have learned that we have like, in the case of resistance we had like current and EMF was in the same phase. This is, in the case of inductor what we have, potential leads current by 90 degree, and in the case of capacitor, let us suppose this is, and current is over here. So we see that there is phase relation between current, between voltage in the case of inductor, capacitor and resistance. See what we have, let us suppose this is potential across inductor, this is potential across capacitor, this is potential across resistor. So we see that when we have to calculate total potential across this LCR circuit, we cannot add algebraically because there is phase difference between them. We see that, see, let us suppose VL is greater than VC. See what will happen, the resultant will come to this side, it will be inductor dominated circuit. See what it will become, this is VL, this is VC, and over here what we have, this is VR. Then the net potential due to LCR circuit will be what? This is the net potential. It is not added algebraically because it has phase difference between them, and though then how they are supposed to find total potential across LCR circuit? See, it will be like this. It will VR square plus VL minus VC whole square. And we know that, see, this is what? This is I into Z. This is what? VR is what? Potential across resistor. VL is what? I into XL. This is I into XC. So what we have? This is Z. I comes out like this. We have, this is R square plus XL minus XC whole square. This and this get cancelled out. This becomes, see, this is total resistance in the LCR circuit, and it is denoted by Z, that is impedance. Yes. total resistance in the LCR circuit will be equivalent to impedance of that circuit. That is, we have inductor, we have capacitor, we have resistance. It all result to, we suppose we take out total resistance, it is coming out to be Z, that is impedance, and it will be equivalent to what? The square of resistance plus difference in the XL minus XC whole square. What is XL? XL is basically, we have inductive reactance, and what do we have XC? This is capacitive reactance, and XL we know that it is equivalent to what? Omega into L, that is 2 pi nu into L. XC is what? 1 upon omega C, and this is 2 pi nu into C. That's all for today. We'll meet in the next class. You need to go through AC1 and AC2 to get the clear grasp of the topic. We'll meet in the next class. We'll go to the numerical and all in the next topic. Thank you for today.